Hello, everyone. My name is Alex Takla. My mentor is Ballet Wen. We are both from the University of Michigan. And today I'm going to be talking to you all about our research involving high-wave number study solutions of two-dimensional Rayleigh-Bénard convection between stress-free boundaries. So before we go over that, I think it's important to go over some applications of convection and what exactly convection is. So in fluids, heat is really transferred via two mechanisms primarily. We have conduction and we have convection. Conduction involves heat being transferred by the particles' vibrational motion about their equilibrium position, whereas convection involves heat being transferred by a bulk movement or mass flow of fluid. Whenever I think about convection, I typically think about a teapot, mainly in the fact that the water or fluid closer to the hot plate will be warmer and result have a lower density and will want to rise to the top, and in return push the cooler, more dense water to the bottom, and will have this sort of cyclical effect, or these convection cells as they're called. Two main applications of convection include the movement of the tectonic plates in our Earth and energy transfer in stars in this convective zone right here. And actually, without the additional effects of energy transfer via convection, we would not have any stable stars and life would not be possible, actually. So what exactly is Rayleigh-Bénard convection? It's the sort of natural convection that occurs between two vertically separated boundaries with a negative temperature gradient. The key there is the negative temperature gradient. The bottom plate must be hotter than the top plate in order for convection to occur. So in studying Rayleigh-Bénard convection, there are typically two boundary conditions to consider, excluding the natural boundary conditions, which we'll go over on the next slide. So the two boundary conditions that you can choose between are the no-slip boundary conditions, meaning that the fluid at the top and bottom boundaries will move at the same speed of the plates themselves, or the stress-free boundary conditions, meaning that the top and bottom plates, or the fluid at the top and the bottom plates, will not apply any stress to those plates. So our problem can really be reduced to the following three equations. The first two consist of the Navier-Stokes equations. The first one being nothing more than a statement of Newton's second law for fluids, basically F equals ma for fluids. The second equation is a conservation of mass equation. It states that the mass or the fluid in our problem will not be created or destroyed. The last equation is the diffusion equation. This governs how the temperature evolves in position and in time. We do apply the Boyce-Kness approximation to the problem, which states that density variations due to temperature are only really relevant in the buoyancy gravity term. Variables in the problem have been non-dimensionalized in terms of the layer thickness h, the thermal diffusivity time h squared divided by the thermal diffusivity kappa, and the temperature difference delta T. The natural boundary conditions in our problem include a fixed temperature difference between the top and bottom boundaries. Mainly the bottom one will be hotter than the top one. No penetration boundary conditions, which means that the fluid cannot escape our problem, and that it's gamma periodic in X, meaning that a point along this horizontal boundary will continue over on this one. So our problem is continuous in our domain. The boundary condition we choose to study in the problem is the no stress boundary condition, denoted by these partial derivatives going to zero at the boundaries. So in Rayleigh-Bénard convection, or at least in our model, there are 5 parameters to consider. The 3 in blue are the ones that we can control in our problem. This includes the Rayleigh number, the Prandtl number, and the aspect ratio. The Rayleigh number can be thought of as a measurement of how chaotic the flow is or how turbulent the flow is. The larger the Rayleigh number is associated with a larger turbulence or a larger amount of chaos, you can call it. The Prandtl number is simply the ratio of kinematic viscosity to thermal diffusivity, and the aspect ratio is simply the domain's width to height ratio. Now, the 2 parameters in red are ones that we cannot control. These are the dependent ones, which include the Nusselt number, which is very important to our problem. It measures the effects of convection. It's simply the ratio of the total heat flux to conductive effects. So the larger the Nusselt number, the larger effects of convection. The Reynolds number is simply the ratio of the velocity to the kinematic viscosity times our length scale h. So a big question in Rayleigh-Bénard convection is, how does the Nusselt number scale with Rayleigh, Prandtl, and the aspect ratio in the asymptotic regime? Mainly, can we write the Nusselt number as a function of the Rayleigh number, the Prandtl number, and gamma as Rayleigh goes to infinity? Two theories have been suggested. The first one includes the classical scaling theory, which suggests that the Nusselt number goes as Rayleigh to the 1/3. This was proposed by Priestley and Malthus, and their main argument was that at infinite Rayleigh, our heat flux should be independent of the vertical separation of the two plates. Ultimate scaling was proposed about 10 years later by Spiegel and his postdoc, suggests that the Nusselt number scales as Prandtl to the 1/2 times Rayleigh to the 1/2 as Rayleigh goes to infinity. And the following argument they made was that the heat flux should become proportional to the fluid's free fall velocity, resulting in this 1/2 scaling of the Prandtl and Rayleigh numbers. So why are we studying the steady state? Before we go over that, though, I want to start this video, and I urge you to pay attention to it because it's a big point about this. Mainly in the fact that our steady solution shares many features with the turbulent solution after a sufficient amount of time has passed. You'll see that this video of the time-dependent solution will look a lot like our model here. Additionally, the steady state forms the state space skeleton of turbulent dynamics. And most surprisingly, or most interesting, is that in a recent study, it was found that the steady state is the one that totally maximizes the heat transport, which is typically not intuitive. One would often think that a time-dependent solution would have an overall greater heat flux, but that's actually not the case. So previous work in the stress-free case was done for low to moderate wave number solutions, basically for a wave number k defined as 2 pi over gamma less than or equal to 10. And as we see in the study, it was focusing on the scaling of the Nusselt number and the Reynolds number. So some key features of this graph: if we were to fix our wave number and basically follow increasing Rayleigh number data, so following from orange to this yellow to purple, we see that as Rayleigh approaches infinity, for all these wave numbers, it approaches some constant, depending on what choice of k we choose, of course. And this dashed line denotes this constant. It's called the Cheney-Cox prefactor. And the fact that Nusselt divided by Rayleigh to the 1/3 goes to a constant suggests that Nusselt is proportional to Rayleigh to the 1/3. Additionally, on this graph, a global maximum occurs at an aspect ratio of approximately 1.9 as Rayleigh goes to infinity. Similarly, the Reynolds number approaches the constant as Rayleigh increases. It does it actually much quicker than the Nusselt case, but again, for larger wave numbers, it takes a little bit longer to reach this asymptotic scaling. But the fact that this approaches a constant suggests that the Reynolds number should scale as Prandtl to the -1st times Rayleigh to the 2/3 as Rayleigh goes to infinity, and a global maximum occurs for this graph at approximately gamma equaling 4.5. So what about the no-slip case? I mentioned at the beginning of this talk that there are typically two boundary conditions to consider: the stress-free one and the no-slip case. It was recently found that in the no-slip case that there exists a second maximum solution. It's a local maximum, not a global maximum as in B, but this local maximum occurs for a relatively large wave number, at least larger than what we've seen in the stress-free one. This occurs at a wave number of approximately 100. So a big question, at least in my opinion, is if we were to increase the wave number to, let's say, approximately 100, will we observe a similar effect for the stress-free case? Mainly, will we observe local maximum features as we increase k to, I don't know, approximately 100? And that is actually precisely what we observe in the preliminary studies of our research for Rayleigh to the equaling 10 to the 8th, 10 to the 9th, 10 to the 10th. So sufficiently large Rayleigh numbers, we observe local maximum behavior at approximately a wave number around 100. So what is our research focusing on? There are mainly two questions that we want to answer. The first one is, well, now that we know that there is a local maximum for the stress-free case, what are the properties of it? Mainly, what is, or how does the local Nusselt number and the local aspect ratio that results in the local maximum depend on Rayleigh as Rayleigh goes to infinity? And the second question is, for fixed high wave numbers, does convergence to classical scaling and the Cheney-Cox prefactor occur for Nusselt and the Reynolds number as Rayleigh goes to infinity? Mainly, we want to see, does Nusselt and Reynolds number, do they observe classical scaling? So does Nusselt go as Rayleigh to the 1/3? And does the Reynolds number go as 10 to the negative first times Rayleigh to the 2/3 in the asymptotic regime? So in our problem, we consider the steady state solution. So all time derivatives or anything depending on time will naturally go to 0. We also define a new variable theta, which is in terms of the temperature field's deviation from the conduction profile, along with using a vorticity streamline function, which reduces our problem from a vector equation to a scalar one. And with these sort of variables that we're using here, we have the new following equation with Dirichlet boundary conditions for all of them. So how exactly do we solve this problem computationally? The first thing we do is that we define the residuals. Basically, all this is doing is moving all the terms of the equation to one side of the equation, calling it a new function, and we want to get these functions to be approximately equal to 0, because then we'll have a solution for it. Then we simply apply Newton iterations, or we basically use Newton's method with the Jacobian matrix in order to minimize the following results, with the ith corrections defined as following. So what are the exact steps of this? The first step is to solve the following Jacobian matrix for each ith correction. So we're solving this problem for each I, so I equaling 1, 2, ... With the ith corrections being defined as the following, and the residuals defined as this from the previous page. The second step is to actually set the psi residual equal to 0, because we can solve this problem directly. And by doing this, we just end up with the Poisson's equation. It's a linear PDE. It can be solved relatively easily. So this is a big reduction in our problem. The third step is to solve our problem on only 1/4 of the domain, since our problem exhibits central equation symmetry. As you'll see, basically our variable satisfies the following conditions, so we can reduce our problem to 1/4 on the domain. The spatial component was discretized in X and the Chebysky series in Z, and the error tolerance, at least for the Newton error, is 10 to the negative 10th, and the GM-res error is 10 to the negative 2. So basically, once our error or once our residuals are of the order 10 to the negative 10th, the residuals are very small. It's approximately 0. So we basically have and call it analytical solution to our problem. So here are the results of what we found so far. So for the local case shown here, we're focusing on the local maximum here. We found that the Nusselt number seems to scale as Rayleigh to the 0.29. This can be seen by the graph on the left. Basically, this dashed line is this equation here, but can probably be seen more easily here. I'm going to explain what this is exactly. This is the local exponent between consecutive points. Basically, it measures the exponent between the following points using a log-log scale. So as we see, as Rayleigh goes to a sufficiently large Rayleigh numbers, this seems to be approaching 0.29, if not slightly surpassing it for Rayleigh over 10 to the 13th. What about the local wave number? How does that scale with the Rayleigh number? Well, from our data, it seems that it scales as Rayleigh to the 1/4. Again, this can be seen by the graph on the left and the graph on the right, this local exponent approaching 1/4 and getting pretty close to it towards 10 to the 14th. So what about the fixed wave numbers that we were talking about? Basically, this time we are fixing the wave number, and it's a relatively small one. It's a relatively large one. The aspect ratios are small, as can be seen here. Well, from this graph here, the data is definitely approaching a constant. And what that means is that This ratio is approaching a constant, so Nusselt seems to be proportional to Rayleigh to the 1/3. And this can be seen more easily from the local exponent graph. All of these data points seem to be converging to 1/3, with convergence taking longer for smaller aspect ratios. As you see, the blue one converges relatively quickly because it's a larger aspect ratio, but the red one takes quite a bit longer because it's a smaller aspect ratio. So what about how does the Reynolds number scale with the Rayleigh number for the fixed wave number case? As we can see, it approaches a constant compared to the Nusselt data extremely consistently, or much quicker than in the Nusselt data. And the local exponent for the Rayleigh number seems to go as Rayleigh to the 2/3, as can be seen here, and the convergence of the local exponent to this dashed line denoted by a 2/3. So conclusion. So for the local maximum properties, we found that the Nusselt number seems to go as Rayleigh to the 0.29 as Rayleigh goes to infinity, and the local wave number seems to go as Rayleigh to the 1/4 as Rayleigh goes to infinity. What's really important about our results is that it is actually extremely consistent with the no-slip case studied by Ballet-Wen. For fixed high wave number properties, we found that both the Nusselt number and the Reynolds number exhibit classical scaling, mainly that the Nusselt number scales as Rayleigh to the 1/3, and that the Reynolds number scales as Prandtl to the -1st times Rayleigh to the 2/3 as Rayleigh goes to infinity. So what we're currently working on right now is how does the local Reynolds number depend on Rayleigh as Rayleigh goes to infinity? And what is the Prandtl dependence of the local maximum solution? Additionally, in terms of the fixed high wave number properties, we are continuing computations for aspect ratios equaling 0.08, 0.1, 0.4, and 0.5. And that is all I have for you. Thank you so much for listening, and thank you for allowing me to have this opportunity to present my research.